Okay, we're live. All right. Thank you so much, everyone, for joining. Lukman, how are you doing today, my friend?
I'm good. Thanks, Jonathan. Thanks for having me here.
Absolutely, absolutely. Well, a lot of us here are super excited about machine learning, of course. And why don't you do a quick introduction to yourself as part of your inaugural entrance into Google Cloud Platform Online Meetup number 8?
Sure. So I am a part of the solutions architect team here in the Google Cloud. I am actually what we call a noogler. So I've been at Google just a short time, just a couple months. But I have both a professional and an academic background in machine learning. And I'm super excited to be joining Google and helping to bring Google's machine learning technologies to our customers. And so my role here at Google is to both on the sales side to help our customers as they're transitioning into cloud and implementing machine learning solutions on Google Cloud, as well as crafting solutions that we publish as papers around specific problems that show examples of how to solve machine learning problems using Google Cloud technologies.
Yeah, that's great. Yeah, and Lukman is relatively new, so for those of you listening in, don't give him too hard of a time. He's only been around for a couple months, but
I appreciate that.
yeah, the goal here is just, hey, let's keep this informal. Remember, this is a online meetup, so it's going to be informal. Just let's have fun. So please go ahead and ask us questions, and I want to thank Viral for helping us on the chat. Lukman, you ready to go?
Yep, ready.
Let's do this. All right.
All right.
So here's the agenda.
So yeah, we're going to start very briefly with the basics of machine learning, just a very high-level overview, what it is, why you should care, how it works. We're not going to spend that much time on that, but I just want to level set and make sure everybody's on the same page. Then we're going to cover the different ways you can leverage the Google Cloud and TensorFlow for machine learning, and the bulk of the presentation will be about that. So we'll start with a couple quotes. This one's from Eric Schmidt, executive chairman of Alphabet, which is the parent company of Google, as you know. He said this last year at GCP Next, our largest annual cloud conference. Machine learning will be the basis and fundamentals of every successful huge IPO win in 5 years. So clearly, if Eric is right, machine learning is something that everyone should be thinking about now for the strategic direction of their business. And then Mark Cuban one-upped him and said, artificial intelligence, deep learning, machine learning, whatever you're doing, if you don't understand it, learn it, because otherwise you're going to be a dinosaur within 3 years. So hopefully that helps to motivate our conversation.
Yeah, I think I'm going to do some kind of ML startup and bring it to Shark Tank, since he's a
So yeah, but smart business people know that AI and machine learning are the future of business, and particularly here at Google, our strategy now and in the future is highly focused on AI and machine learning. So let's briefly review the sort of what, why, hows of machine learning. Machine learning is a process of building algorithms, or we call models, by learning from data. Actually, can you go back to that one more slide back?
Yep.
Yeah. Yeah. So it's a way of extracting insights from data, and historically those have been generated by humans. And the reason why we're interested in machine learning is because machines can generate these insights faster, cheaper, and better than humans by discovering patterns in data. So the difference in machine learning is that it's the algorithm itself generating the insights from the data, not the human being. Next slide, I'll give you sort of a personal view of from my own history as a computer scientist. A little bit idiosyncratic, but go ahead, next. If you know anything about traditional theoretical computer science, it's based on models of computation that operate in the symbolic space over collections of symbols. So the way I think about machine learning is that it's a generalization of that symbolic model of computation to operate over vector spaces. So rather than providing symbolic input, you're providing vectors as inputs. Rather than having an algorithm that's programmed by humans, you have algorithms that learn from experience But there's still the analogous mechanisms of memory and algorithms. In the case of machine learning, the algorithm is the model itself. It's the thing that is taking the inputs and processing the data and outputting the answers that you're looking for. This is obviously a very deep topic, and I won't spend more time on it, but I thought I'd give you kind of some food for thought in case you hadn't thought about machine learning in this way.
Yeah, I think one thing that most people don't realize is machine learning, a lot of the algorithms, mathematics behind a lot of it has been around for many decades. It's just now that we have all this compute power to actually do something interesting and meaningful with it.
Yeah, that's right. So my personal history of machine learning goes back to the 80s as an undergrad at MIT when I was working with, that's funny, the guy's name is Michael Jordan. He's known as the Michael Jordan of machine learning.
Number 23.
Anyway, he's actually a seminal researcher in machine learning. He's now at Berkeley, but yeah. So I mean, back then we were doing very much similar things to what's happening now. With we didn't call it deep learning because we weren't able to get that deep. We were only able to do 3 layers, given the compute power that we had at the time. And so with the advent of GPUs, that's been probably the most key thing that's really propelled the field is the availability of cheap computing power. The kind of thing that when I was in grad school would have required a supercomputer account. Now you can have that on your desktop. So let's talk about how to leverage machine learning using Google technologies. It's just worth highlighting Google's machine learning credentials. So this is, machine learning is central to our company culture here at Google. It's currently used in almost every one of our products, actually. So in 2016 alone, we published hundreds of machine learning research papers. We spoke at top-tier conferences about machine learning over 300 times. In fact, at the most popular academic conferences for machine learning, the submissions currently from Google are by far the largest of any other group. So Google's made a huge foray into the academic side of machine learning. We've essentially hired up the many hundreds of the top computer scientists and machine learning scientists. When you use Google Cloud's machine learning platform, you're benefiting from all of that expertise and all of that experience actually using that machine learning in Google's products.
Yep.
So go ahead.
Yeah, I was just going to say one thing I found really interesting was that I think over the last 3 years, we've seen an exponential increase in the number of machine learning models that exist in our repository at Google, which means that machine learning is, one of the fundamental technologies we're leveraging in order to automate and improve the way that we interact with users across all our products.
Yeah, that's right. So, it's used in Gmail spam classification. It's used in Google image search and almost every other product that we have. So the rule number 1 of machine learning is don't build a model if you don't have to. Building a model is very hard and complicated and requires a lot of expertise. And if you can leverage an existing model, of which we have several that we make available through our cloud APIs, then you should do that. So it's important to be aware of the APIs that Google makes available. If you can leverage one of our pre-trained models, then you should do that. So we'll quickly go through the various machine learning APIs that Google offers currently. Go to the next slide. So we have 5 different APIs, behind each of which is a state-of-the-art machine learning model pre-trained by Google experts. And these are available using standard web APIs, so using REST calls, for example. And they're trained on our massive data sets that we have available here at Google using the full power of Google's compute resources. So again, it's good to be aware of the services that are currently offered by these APIs, because if you can use them, then it's going to be a much quicker path to you solving your problem than certainly than building your own model. So here, let's go through just a quick tour. We have the Vision API, which is basically an object recognition API. It also does facial detection, sentiment analysis in the image to tell you if a person that it detects is happy or sad. It does OCR on images, so it extracts text, and it can also detect inappropriate content, i.e., things that would not be safe for work.
Yeah. For me, the Vision API is, I mean, you would think it does pretty simple things, but I was really surprised by the accuracy as well as the thoroughness of what we can detect. So, for example, I was working with a little startup. They do interior decoration, and we had a discussion with them. The first thing they said is, "Hey, I don't think that your model is going to be able to detect what we need." And what they wanted was they wanted to determine what room in the house that they were they were looking at. So they would have a picture of, let's say, a bedroom, a dining room, a family room, and they wanted to suggest different tones of colors and styles based on what the room was. And they said, I really don't think that Vision API is going to be able to handle that. So, in that same meeting, I was like, let's just try for fun. And
Right.
next thing you know, I mean, it was detecting the bedrooms, the master bedrooms, the bathrooms, and it was giving them everything they needed. And from that meeting, they were able to determine that they did not need to build their own model. So the Vision API actually is very comprehensive, and surprisingly to me, like it has so much information behind each image that it can process.
Yeah, it's amazing the different data sets. So I know, for example, there are 1.5 million different logos that are part of the training set. So it'll identify logos of of companies or brands. And another thing that it's trained on are landmarks. So if you just take a random picture somewhere in the world, if that picture is has any popularity to it because it's something that other people take pictures of, then it's very likely that the image API would detect that location or detect that landmark.
Yep.
So then the next API we'll talk about is the natural language API, which is obviously all about understanding text. So it extracts and labels keywords. It does sentiment analysis to determine if what is being said is positive or negative. Obviously, so this could be, for example, useful for analyzing what people are saying about your products in large scale, in comments to forums or obviously in tweet streams or Facebook comments and so on. And it supports multiple languages and does advanced syntax analysis. So again, the kinds of things you could do with this are really only limited by your imagination. It's an extremely powerful API, and it's been broadly used at Google as well for lots of different internal products.
Would this be a good platform for building a chatbot? I know there's a lot of different ways to do it, but is this one of them, or would this not be the best?
This could be a component of a chatbot solution. In general, building a chatbot also involves constructing dialogue, right? Because a chatbot by definition is something that you interact with, and you want it to respond to you, and then you respond to it. There is another API that Google just acquired through acquisition. We bought a company called wit.ai. We're not going to mention that in this presentation, but that company and that API is specifically designed for dialogue. And that API is also available and would be best suited for chatbots.
Got it.
But yeah, we actually don't have a slide on wit API. We're trying to hit all of the high level APIs here. There's a lot to cover. So then again, in the realm of language, we have a speech API, which is used for voice recognition. So this is the same technology that powers Google Voice Search and Google Home, and supports over 80 languages. It's really good at handling noisy audio, and you can provide it grammars or basically hints that for words that you're expecting to detect, and it will recognize those. So there's a huge number of different applications that this could support as well. So for example, we work with folks that have call centers that have recorded interactions between their agents and customers, and the speech API can be used to automatically transcribe those. And then you could take those transcriptions and then run them through the natural language API to detect sentiment, for example. So using that kind of pipeline, and this is a very common scenario, right, where you chain these APIs together or mash them up, if you will. You could automatically tag individual calls based on individual calls into your call center based on the sentiment of the call. You know, was the customer irate or happy or so on. And then another API that's related to language, obviously, is the translation API. And again, this is the same API that powers Google Translate on the web. It's able to translate into over 100 languages, thousands of language pairs. And we just made a major upgrade to this towards the end of 2016 using a new neural net-based backend. And had a dramatic increase in accuracy. So I don't know if you've tried the Translate API. You can do that on almost any web page. You can, if you go to a foreign web page, you'll have in Chrome, I should say, you have the ability to translate that. The translation, and if you try it, is remarkable. It really is. There's been an amazing advance in this.
It works.
Just in the past year.
Yeah, I was in Japan and I was eating sushi, and there's like a couple pieces of sushi. I had no idea what it was. So I told the chef, I said, hey, you know, I was just pointing at the sushi and I told him to say what it was. And then it translated it for me and it worked perfectly. So yeah, it was sardines, by the way. I was like, okay, that's pretty interesting.
Right. So yeah. So another, this is kind of another mashup, right? You know, we have a demo that we gave it Next, where called the Thing Translator, where it starts by taking a picture of an image, which is passed to the Vision API, which obviously then returns back labels, possible labels for that image, or to identify what object that you just pointed your camera at, and then passing that again through the Translation API. So effectively, it's like a handheld translation device that you could go point at signs in a foreign country and have them translated on the fly, for example. Super cool. So then finally, we have the newest API in this bunch, the Video Intelligence API, which we just rolled out as the beta in our Next 17 event, which just happened in San Francisco earlier this month, just a couple weeks ago. And this is can be used for extracting insights from video. The first application of this, or the first set of functionality that we rolled out in this, is label detection. So essentially, it detects entities, again, obviously objects or recognizable things that are in the video, returns that back as well as the timestamp associated with that entity, so when it appeared in the video stream. And one of the obvious use cases for this would be for video search. So you could search for dogs in your collection of video and get a list back of every video that had a dog, and also the actual timestamp when the dog showed up in the video. And it's worth noting that you can try all these APIs for free from your browser. So if you go to cloud.google.com, you can test these APIs out, each one of them, by dragging and dropping things or typing stuff into text boxes and just playing around.
Yeah, this is how most of our customers get their feet wet, is they just go to the website and maybe upload a picture to see how well it performs. And after that, they'll start building and modeling some software around the APIs. But, this is a good first step to get some education on how our APIs work.
Yeah, and as we said before, if you have a machine learning application and you're not sure, or you think that maybe one of our existing APIs could cover your use case, then you should always try that first. Having said that, there's obviously only so much a pre-trained model can do, and so we're going to talk now about building your own model and the range of technologies that Google has available for helping you do that. So you could go to the next slide. Building a model, a machine learning model, requires typically three things. You have to have data, and usually a large amount of it. you need compute power, and obviously you need talent. So you need typically a data scientist and or a data engineer. The reality is that building machine learning models is still something that experts generally need to do. And so if you give a team of smart data engineers the right data and access to a bunch of compute power, they will eventually, come up with a machine learning model, but it could take a very long time. And one of the things that Google has focused on with our machine learning technologies is ways to accelerate that process and allow you to harness the scale of the compute resources at Google, as well as building an ecosystem of tools to make that process much easier and faster. So Google's tools include obviously Tensorflow, which we'll talk a fair bit about later, which is a general robust framework for building machine learning models. We also have Data Lab, which we'll do maybe a quick demo if we have time of, which gives you an integrated development environment for building or testing your models. There's Cloud ML Engine, which is a managed compute platform. It's kind of like TensorFlow as a service in the cloud, which allows you to train your models at scale and harness, again, the full compute power of Google's cloud to do that. And then we have a full big data stack, which allows for the hard part, namely data ingestion and transformation, which is typically the thing that takes the most time when you're doing this stuff. So let's take a look at each of these a little bit more closely. We'll start with compute.
Yeah, I would love to get to the demo. So let's maybe try to speed through some of this.
Sure. Yeah. So look, the big challenge with training machine learning models is training time. Basically, if you don't have a lot of compute power at your disposal, then you may be looking at days or even weeks or months of time to train a model. So that's where a machine learning engine or ML engine comes in. It allows you to train models at scale, leveraging the full power of the Google compute infrastructure. So again, typically the machine learning workflow using ML engine will involve you developing your model first using TensorFlow and running it locally. So testing it out and making sure that it's correct, that it's processing the data correctly, and trying it on some small data sets just to make sure that you're getting sensible outputs. But then once it comes time to train that model at scale, you would upload that model to Cloud ML Engine. And there, as long as you've constructed your model correctly, and we'll talk a little bit more about that, then automatically Cloud ML Engine will scale your model and train it on potentially hundreds of workers. I mean, again, this is something that you can control as a parameter, and you can decide how many workers you want.
Yep.
And then finally, and we won't talk much about this, but once you've got a trained model, then obviously you want to use it. There's a framework called TF Serving, TensorFlow Serving, which allows you to take your trained model and deploy it just about anywhere. So you could deploy it on a phone or in your own website, your own web application. And that's the beauty of TensorFlow, is that it'll run on any device. And so once you've built your model, you could use it again on a phone without having to connect to the cloud or in any other context.
Yeah, so Lukman, I think one thing that's interesting is, we do have customers who run their own TensorFlow, I'll call them clusters or environment with our compute engine. And yes, absolutely, you can do that. There's a lot of operational complexity and cost to building out your own TensorFlow environment. Cloud ML is really for people who want to focus on the learning, the training, and uncovering the meaning behind the data quickly by just pointing their training sets to an API, as opposed to having to set up all their infrastructure just to get the training done. So, there are multiple ways to skin a cat, and the Cloud ML is just trying to reduce the barrier of operationalizing the TensorFlow environment.
Yeah, that's right, Jonathan. As everybody knows, TensorFlow is an open source framework. So all of the capabilities here that we've described are built into the open source version of TensorFlow. And you can certainly set up your own distributed compute stack and run that locally. But it's more complicated, and you're basically not leveraging in that case all of the work of the Google engineers behind the scenes who make it easy and who maintain maintain that large technology stack to make that happen on Google Cloud. And in addition, it is really possible to scale, to train these models on thousands of worker nodes if it comes to that. And most people don't have that kind of infrastructure available locally. So just as a point of illustration, we'll use an example my colleague on the solutions architects team, Corey Elston, created, which is a model that, given historical stock data, would predict whether the S&P 500 was going to close up or down with 70% accuracy, which is not bad.
That's amazing.
Yeah. That if you really could use that to trade stocks, you'd probably do pretty well.
You wouldn't be working here.
So this model had 4 hidden layers, each containing 1,000 nodes. And when using one worker, so this is equivalent to running it locally, it took 5 days to train the model on the full data set and to achieve that accuracy. So if you think about it, that makes it really hard to iterate, right? I mean, if every time you make a change, it takes 5 days to validate what that change is, or if you're doing hyperparameter tuning, which is something we'll talk about later, like by adjusting a parameter, a learning rate, or the number of hidden layers, or the batch size, or whatever, and you have to wait 5 days to validate whether that change makes a difference, it's going to be a very slow process. In fact, this is kind of how it was for me when I was in grad school. But the beauty of ML Engine is that it allows you to scale up, and this just shows the sort of linearity associated with the scaling. So as you add worker nodes, you get this corresponding decrease in training time. And with 96 workers, it turned out to take only 1.25 hours to train the complete model. So that's a huge difference in terms of practical, the ability to practically create a model. If it only takes an hour to turn around and train a model so that you can test a hypothesis or try different data or do hyperparameter tuning. And moreover, Google Cloud ML actually will do the hyperparameter tuning for you. We'll talk about that just in a second. So what you're getting in the ML engine is access to large-scale, high-end, GPU-powered computation. And in addition to that, we've been working internally, and we have been using internally a new kind of compute hardware called tensor processing unit, which is actually it's similar to GPUs, but it's optimized for the predict part of the problem. So whereas GPUs are better for focused on training, once you've built your model and you're running it in the cloud and you want to rapidly perform predictions, these tensor processing units that we've been working on will make that extremely efficient. And again, efficiency is a key thing here, because when you're deploying these models at scale, you don't want to spend millions and millions of dollars processing large scale input, and that's where the efficiency and the energy consumption of the hardware actually makes a huge difference. And Google's put a lot of research into making really efficient numeric processing units. We call these TPUs, and we're just about to roll those out.
So, all I know is there's a bunch of engineers that are locked up in a basement working on this. And I know that because I keep asking about, what's the status. And those 5 bullet points you have there is about all the information I know about TPU. So a lot of customers ask, hey, what's going on with TPUs? The answer is, I have no idea. No one knows. And only a select few know about what the status is. But yeah, just stay tuned. It's really exciting. And the results that we have so far is just incredible.
Yeah, so we've talked a little bit already about hypertuning, but just to reiterate, this is a service that's provided by ML Engine. Basically, you describe the ranges of parameters that you want to search over. So these could be, for example, mini batch size or learning rate or number of layers, density of layers, and so on. And Google has a search algorithm that we've developed here that searches over that space and does, again, in a distributed way. So it can happen really, really fast. And instead of what it used to be the case, where it would take you weeks or months of running these models over and over again to find the right the learning rate that optimizes your training, or the batch size that optimizes training, you can get those results back in just a matter of hours. So super powerful and a very cool feature. So again, in summary, Cloud ML Engine is basically TensorFlow as a service in the cloud. So we take care of the infrastructure, the monitoring, the logging. We allow you to version your models. We can talk about that, but basically you can store different versions of models and call on those for either training or prediction. And we manage the scale out up to 100 workers. In fact, I think there's custom tiers that allow you to go beyond that. And then when you're done with training, it's very easy to deploy those models that are trained in the cloud and live in the cloud. Very easy to deploy them for prediction as well. Or for that matter, you can download those models and deploy them anywhere you want. So there's no lock-in. But it's not like as if once you train your model in ML Engine, you're stuck there. You can still download your model and deploy it as you wish.
Okay. You think we can breeze through the data part?
Yeah, I mean, in fact, why don't we skip ahead and just take a quick look at, let's skip the professional services stuff too. Just know that Google has professional services available to help you if you would like some, Google expertise to help you, figure out your machine learning strategy, or help you with the actual training, or even developing your own core competency in machine learning. Yeah. So why don't we, the demo is going to be hard. Okay. The data lab demo is going to be hard because you control the screen.
Yeah. Okay.
So we'll skip that too. But if you go to Google Cloud site, check out Data Lab. Essentially, like I said earlier, it's a Jupyter notebook that's already set up with all of the libraries that you need for training using TensorFlow. It has access to BigQuery, and it just makes it really, really easy to iterate very quickly and to train your TensorFlow code. All right. So yeah, let's move on to TensorFlow. So as many, if not all of you probably already know, this is a free open source machine learning framework developed by Google Brain. It was open sourced in 2015. It is now the most popular machine learning framework, at least as measured by GitHub forks and by GitHub stars. The popularity of TensorFlow also means that you can tap into a very large and growing community of developers to reach out to for help. On top of that, the technology itself, because there's so many contributors, both obviously inside Google, but also outside Google, the TensorFlow stack is evolving extremely rapidly. So these are all good reasons why TensorFlow makes sense to use. I mean, there are a lot of other frameworks that are out there, but by using TensorFlow, you're really tapping into a massive amount of investment on the part of Google. And so even though we just went 1.0 with TensorFlow just earlier this month, actually, we're really, really rapidly iterating here at Google on TensorFlow, and new APIs and new features are coming out almost every other month.
And I know my customers who talk about, I mean, they have decisions to make in regards to which platform they want to use. I think one of the reasons they like TensorFlow is, besides the support and the open source contributions from many companies, is that does work across many different platforms, right? and being able to train a model and leverage it on a variety of platforms reduces the amount of work that they have to do to really find a model that's useful across different environments. So, Lukman, I want to ask you, like, which platforms have you used, or why would someone want to use TensorFlow instead of some of these other platforms?
Well, so I've personally used on this list scikit-learn, which is
Mhm.
a very common Python machine learning framework. I played around with Torch. I've dabbled in MXNet, not done too much with that. And I've also used, which isn't on this slide, the Spark MLlib,
Mhm.
which is really easy to use in the context of a Hadoop cluster or a Spark cluster. So the reasons why personally why I think TensorFlow is a good way to go is it is to your point, Jonathan, it really offers you the most flexibility. You can run it on almost any system. The models that you get out of it can be run again on actual mobile devices. And moreover, although I would say core TensorFlow, like vanilla TensorFlow, is a relatively low level API. There are many other higher level APIs that have already been built on top of TensorFlow and or are migrating to TensorFlow. So Keras is another example that we're going to talk about a little bit more as well later.
Cool.
Keras is a very popular Python API for machine learning, and the gentleman who wrote Keras is now works for Google, and we're basically importing Keras over to TensorFlow. So again, I think it's the flexibility, it's the power to run an ML engine at scale, so that you don't need to concern yourself with the underlying compute infrastructure. And I run TensorFlow at home on my own desktop system with the GPU on it, and it runs great. And actually, with a reasonably powerful GPU, you can do real, substantial model development. But then, obviously, for a business, in a business context, when you want to run that, when you want to run your model at real scale to solve real big business problems, you're going to need either to build your own compute infrastructure or harness the Google Cloud. And why not harness the Google Cloud? So anyway, I think it's a good investment. I know you know that Google is going to be 100% committed to it going forward, and it's open source. So you're, like we said, you're not locked in.
Right.
So those are all good reasons. And here's another good reason, just from a sort of technical development standpoint, is an example of why TensorFlow's APIs are so powerful. Here I've taken the same code, which is building a model, I think, that predicts based on the square footage of a house, the price of the house, I believe. I think was the original model here. But what it really shows is swapping out a linear regressor that's kind of doing the core prediction, or is the core model, for a more complex model, a deep neural net regression model. And how easy it is to do that, right? So with basically replacing one line of code in this TensorFlow-based model, I'm able to first test my model on a very simple linear regression model, and then establish a baseline for performance. That's good. That model is going to train extremely rapidly, and provide me a baseline. And then by changing one line of code, now I've got a linear. I've got a deep neural network. And moreover, I can, by changing the hidden units parameter, I can adjust that easily, the number of layers and the number of units in each layer. So
Yeah.
this kind of illustrates the power of the APIs.
Lukman, in your opinion, what is your type of workflow when you start training and doing machine learning? I know obviously linear regression or just linear model is kind of the first approach to setting a baseline, but because there are so many different types of algorithms you can use to train models, are you going from linear straight to neural? Are you doing support vector machines? Like, what is your, I guess, thought process in terms of how you want to start slowly improving the model?
Yeah, well, I guess the short answer, it really depends. It depends on what kind of data set you're looking at. I mean, obviously, for image-based data sets, typically you're going to use a convolution net.
Mhm.
In fact, a linear regression that won't always even be an option. I mean, it's not, I guess it's not true. Like, most simple image sets, you could train them using a linear regressor. It's not going to give you a very reasonable baseline, though.
Right.
I mean, it'll validate that your model is that the rest of the code around your model is working. It's not going to give you any kind of realistic error as a baseline. So in that case, I might go straight to a convolutional net. There's just no point in doing the a little bit of extra work necessary to set up the linear regressor. So yeah, it really depends. I mean, ultimately what drives the choice of model is the problem domain and the data set itself.
Yeah.
Right. The data is king in the world of machine learning, and you start with so again, in a neural network, I mean, sorry, in a natural language processing model, it may be appropriate to use a recurrent neural network like long short-term memory, for example, is a common sort of neural net architecture for processing sequences. But it depends. So I mean, again, in general, for very sort of like simple flat data sets, real valued numbers, yes, what you said is correct, that it often makes most sense to start with a linear regressor as a baseline, and then look at more complex models. There's something also called the wide and deep network, which combines a linear regressor with a deep neural net, and that's become a very popular model here at Google. Oftentimes, that will be the best approach to a problem that you would normally have applied linear regression to.
Yeah, and we're gonna have to have you do a deep dive on wide and deep sometime in the future, Lukman.
Yeah, no, wide and deep is worth definitely an entire meetup. It's become a really popular approach. So we're starting to run low on time, and there's a bunch of other stuff I want to talk about with respect to the APIs. I'm just going to breeze quickly over TensorBoard. Just know, if you haven't used TensorBoard, that it's a very, very cool tool for visualizing your TensorFlow graph, and also then during the training process for gives you nice graphs of the error rate, and it's a very easy way to explore your model as you're training it and after you've trained it. But I want to first give you a pointer to the TensorFlow Dev Summit. So we've held these. I think this was maybe the third one. At least this. I know there was one last year, but in any case, the 2017 Dev Summit just happened a few weeks ago. And if you Google TensorFlow Dev Summit 2017, you'll find a site which has links to all of the presentations. So folks like Jeff Dean and the entire CloudML team, as well as the guy who wrote Keras, all get presentations and talks, and really fascinating stuff. Ton of great information about developing with TensorFlow, the latest developments in TensorFlow technology stack, and the future direction of TensorFlow as well. So I highly recommend you check that out. And so one of the primary developments that's occurred in TensorFlow over the last year, I would say, is, as I mentioned before, the development of higher level APIs. So the standard API for TensorFlow uses either the Python front end or potentially the C++ front end. But again, I would characterize those APIs as relatively low level APIs. I mean, you have to do a lot of boilerplate code to set up your model and get it to run. And so there's been a large development in higher level APIs to make the process of developing your model much, much more rapid. One of those, for example, is the Layers API, which makes it really easy to define your TensorFlow graph in terms that are natural, basically, for a deep learning model, namely as a stack of layers, using predefined layers that are commonly employed in machine learning models. So we'll take a look at what that code looks like in just a bit. The other interesting new high-level APIs are the estimator class, which I'll give some more detail about, and the Keras API, which I also mentioned. So Francois Chalet, who's the author of Keras, as I said, works for Google now, and the Keras API is being incorporated into TensorFlow basically as a high-level API that gives you an option for defining your models, or you can take, if you already have a model that's written in Keras without changing it at all, basically you can run it on TensorFlow, on the TensorFlow stack. You could deploy that Keras model into ML Engine and run it on the cloud. That capability is actually coming out in TensorFlow 1.1, which we're now at 1.01, and the historical pattern has been a point release every 6 to 8 weeks. So we should expect in a month or two that 1.1 will be released with this Keras integration available.
All right. So Lukman, we got 10 more minutes. How do we
All
want
right.
to go forward?
I think we're doing okay. I think
Okay.
we'll keep going here. And then on top of the estimator class, the estimator API, which again we'll talk a little bit about in a little bit more detail. TensorFlow 1.0 ships with a bunch of canned estimators, and some of those, or the code that we were looking at earlier, basically were examples of those canned estimators. So there's a canned estimator for linear regression. There's one for deep neural networks. There's ones for convolution nets, and several other popular models. Again, the wide and deep model that we also talked about. And so again, these basically make it possible for you to plug in to very, very quickly create models. Again, all you have to plug in are parameters that specify how many layers you want, rather than defining each layer, independently, or even at a lower level defining the actual nodes of the graph as you would do in the low-level TensorFlow API. And what that again allows you to do is evaluate alternative modeling approaches very, very easily. So as we saw in the code just a few slides earlier, I was able to swap a deep neural net in for a linear regressor just by changing one line of code.
With the canned estimators, how do you think that addresses like 75% of the use cases? Well, what, in your opinion, how often do you need to do a custom estimator?
Yeah, that may be close to the truth. 75% may be, in fact, pretty close. Again, it depends, on how sophisticated you want to be. If you're doing, fundamental research in machine learning, then obviously you're going to be building your own models up from scratch. But in many, many cases, the canned estimators are going to serve your needs. So yeah, I would say it's probably not far from the truth that 75% of the time, one of those estimators is going to be appropriate for your problem.
Yeah, I guess I'm a good guesser. But yeah, I mean, based on what I've been reading on machine learning, these estimators that we have on TensorFlow do address, a lot of the use cases. So I thought I'd throw that out there.
Yeah, that's right. So let's look a little bit deeper at the layers API just to give you an example of what we're talking about here with these high-level APIs. So suppose you're trying to define a convolutional network as a stack of layers that each have different function. Traditionally in TensorFlow, you would have to start by defining your variables and scopes and adding the convolution calls by hand. And it turns out to be a lot of boilerplate code and a lot of, it's a much more verbose process of defining the model. Whereas what the layers API allows you to do is sort of write down the model in the way that you think about them, in code. So each layer of your model can be written down in a single line of code. So you see here, for example, there's one line that defines the convolutional 2D convolutional layer. One layer for pooling, and then very easy to stack those. You can add a dropout layer, and then finally a regular dense layer. And so again, in literally the number of lines equal to the number of layers, I've defined my entire network. And the key thing about the estimator API is that it basically abstracts away a lot of the boilerplate that is involved in training these models. And it also, if you target this API, it will be very easy to deploy your model as a distributed model on ML Engine. So it makes it, if you use the estimator API, it makes it very easy to take that model and deploy it on an ML engine. And we'll just talk a little bit about what the estimator API approach is. So basically, a generic machine learning model will have some inputs, possibly labeled inputs if you're doing supervised learning, and will produce predictions. So if that model is, if you're going to train that model, which typically you will, then this looks a little bit more. You can go to the next slide. Then you're going to have a training loop where you have some mini batch data and you're feeding it into the model and updating the weights. On top of that, you're actually going to need to have an evaluation process to know when your training is complete. Next slide. And so again, this can be done using the prediction output, but more generally, it's useful to have a separate process or separate evaluation graph in TensorFlow that produces your evaluation metrics. Because that evaluation data likely won't fit in memory, you also need to run that as a loop. And so basically, the estimator API encapsulates the idea that almost every model looks like this.
Yep.
And so we draw a box around that and call it an estimator. And an estimator contains the implementation of these loops. And you provide the model as a function, which then returns these training or evaluation or prediction functions. And it's a lot less error prone because it's easy to mess those functions up. And in turn, with those standardized hooks available to the outside, that's what ML Engine uses to run your estimator in distributed across as many workers as you specify. So again, the key thing about this estimator API is that if you wrap your current model, and again, if you've got a current model, it's not going to involve a massive refactoring. It shouldn't involve a massive refactoring. You just may need to group the various functions that you probably already have for doing training, for your training loop or your evaluation loop or your prediction. Wrap those in these standard API method signatures, and then subclass the base estimator class. And then basically you've got a model that now ML Engine can take and run in a distributed way. And again, one key addition to the estimator API is the save model function. So again, if you support that function, then ML Engine can save your model, and you can take advantage of the versioning capabilities that we talked about a little bit before, which makes it very flexible to try different versions of models or deploy different versions of your models for prediction tests and so on. So we're almost done. Just want to talk briefly about kind of what the plan for 2017 looks like. As I said, we're iterating extremely rapidly in all these technologies, and there are going to be a lot of new things coming out almost monthly. However, there is a broad-based common theme to a lot of the new innovations that are coming out for 2017, which is that we're going to blur the lines between pre-trained models and custom models, so that essentially we want to let you take some of the pre-trained models that Google has and add your own training on top of those. So this takes advantage of something called transfer learning, which is basically a way of, it's to take the Vision API, for example, underneath the hood that uses a very large neural network that you can, if you download, you can add your own custom training set to this model, and essentially, without having to train the entire model, you're harnessing the power of those millions and millions of images that are used in the training of that, and then essentially you're transferring all of that knowledge from that pre-trained model that Google provides to your own domain. So again, this is the kind of thing that we're going to be focusing on more and more in our cloud API offerings in 2017.
Awesome. Well, you finished 1 minute earlier.
I'm amazed.
So, yeah, that was
given all that stuff.
So, I mean, Lukman, that was really great. I mean, obviously, you have a very thorough knowledge of machine learning, and I mean, it sounds like we're doing some pretty incredible, making some incredible investments in machine learning. And I'd love for anybody who's still listening to ask some questions with this last 60 seconds left. It's rare that we get someone with so much experience and expertise in this field of study. So take advantage of this. And while we're waiting for questions, Lukman, you want to talk about maybe some interesting machine learning use cases that you've worked on recently? Without,
Sure.
yeah, without
Yeah,
describing specific customers.
without disclosing anything
Yeah.
proprietary. Yeah. So one of the cool things we're working on with is with the folks that are exploring for natural resources. I'm just going to keep it very, very generic. But there's a lot of companies that are out there exploring, natural resources, and they use different kinds of detection devices like sonar or seismic readings and so on to do that. And we're working with customers to take that seismic data and do machine learning on that data to identify patterns that make it that indicate that there might be something interesting under the ground or under the sea. So that's been a really interesting application. And again, there's
Is that
a
mostly deep learning or what type of?
so effectively that data looks like images.
Yep.
You think about sonar or seismic data, it's like radar under the ground, and what you get back is a map, like a 3D map of the density distribution of the rock underneath the ground. And so the presumption is that areas of differing density or pockets of different density would indicate the presence of something that you might be interested in down there. So, the short answer is that it looks very much like an image recognition problem, and we're using models that you might apply to image recognition for that data set.
Yeah, no, that's a good one. And what about during your research? I know you did some research in ML. Anything that you've seen come out and be actually industry useful? Because I know, I mean, when I did research in school, a lot of the stuff was so cutting edge or things that you could never apply, and it never amounted to anything. But since machine learning is kind of the big thing now,
I did my research at the Jet Propulsion Laboratory at NASA, and I was scanning images of Mars from the Viking orbiter.
Oh my gosh.
Which was a data set accumulated in the 70s, believe it or not. That was the far back that we sent this orbiter out to orbit Mars and take pictures of Mars. And I was detecting craters on the surface of Mars, which isn't that interesting. I mean, now it was more like, we had a big data set. It was, a problem that NASA was interested in more generally because they wanted to deploy machine learning based algorithms to the rovers that they knew they were going to send. So this is going back a fair bit, but so the gratifying thing is that all the things that I struggle with as a researcher, like I talked about, taking 5 days to run a model, or really in my case more like weeks, and having a very painstakingly slow process to train and tune the model. This is stuff that can now happen on the order of hours or even minutes.
Right.
And so the pace of progress in the field is really, I mean, it's accelerated, by many orders of magnitude. One other thing that I worked on for many years was speech recognition based dialogue systems.
Wow.
And those are also really starting to become prevalent.
Hey, Lukman, we have a question actually from Haruki, and I think the question is, if you've built and pre-trained your model already, can you just load the model into, I guess, Cloud ML or TensorFlow and just run it if you already have the model built out?
Yeah, that's a great question, Haruki. It's a question that we're really fielding a lot from our customers, and the answer is you will need to make some changes, but they shouldn't be extensive. So one of the changes is something we just talked about at the end of the talk, namely that you'll want to wrap your model in an estimator class. It shouldn't be difficult to do, but basically you want to expose the methods that we just talked about for the estimator. And then the other key change is around the processing of the input. Because the challenge with running your model in a distributed way is how do you slice up all the input? So for the most common case, if you have your input represented in files, which many people do, then say you've got 1,000 files, then the natural thing would be to divide up those files into sets or groups, and then have each worker take some subset of those files and train on them. And so in order to make that happen, you would need to write what's called an input function, which essentially sort of manages that process of dividing up those files. I will say it's really not well documented at the moment. These APIs are very new, and I would love to be able to point you directly to documentation. There's a lot of sample code out there. If you go search for Cloud ML sample, you will find sample code. But it's something that we're actively working on at the moment to document that process of taking your existing model and explaining exactly how you port it to ML Engine. It's a very common question, and we don't have a lot of great documentation to cover it at the moment.
Yep. Okay, well, great. Thanks for asking that question, Haruki. Hope that answers your question. Lukman, we're done. Any last parting thoughts?
No, it's a really exciting time in machine learning. I think I've heard it characterized as kind of like 1995 back in when the web had just come out. It's a wild west, and the opportunities are really endless for machine learning applications. So I really look forward myself to seeing what all of Google's customers come up with using all these tools and APIs that we talked about today. It'll be really exciting to see what comes out.
Yes, me too. Machine learning is going to rule the world. All right. Thank you, everyone, for joining. Really good dialogue and interaction here. Lukman, again, thank you for your expertise here in machine learning and for doing this. Let's talk soon. Wide and deep learning.
All right.
We're going to do that next.
Let's do it.
Right.
Or how do you take your model and deploy it in ML Engine?
That's a good one, and hopefully someone can help us document that process as well.
Yeah, well, that's part of my job.
Oh, okay. All right. Then you got an action item leaving this meeting.
I do, yeah. Thanks a lot, guys.
Okay. Thank you, Lukman. Thank you, everyone. Goodbye.
Yeah.